Picture this. You're standing outside in coastal Maine. It's the dead of winter, classic nor'easter.
Oh, yeah, brutal.
Right. You've got driving rain coming in completely sideways, freezing winds howling off the Atlantic, and heavy, wet snow just piling up by the minute.
Sounds miserable.
It is. So you look up at your house, or, really any of those beautiful 1800s historic homes in Portland, and you consider what is taking the absolute brunt of that storm. There's this one piece of the architecture standing completely unprotected above the roofline.
A chimney.
Exactly.
I mean, it's the highest point. It's completely exposed to the elements on all four sides, 365 days a year.
And most of us look at a chimney and we just see a fortress, right? Like we just see a solid, indestructible brick pillar.
Yeah, a permanent fixture.
Right. But for this deep dive, we are digging into the 2026 archives of select chimney services based right there in Portland, Maine. And our mission today is to uncover why that permanent stone monolith is actually one of the most vulnerable, volatile, and frankly high-stakes parts of a home.
It's such a fascinating look at everyday architecture because it completely forces you to rethink what you're looking at.
Yeah, we're breaking down the hidden science of how they function under extreme stress and the surprising economics of how local experts actually keep them standing.
Because the archives just dismantle that illusion of solid stone. They reveal the invisible physics happening both inside the flue and outside in the weather.
Right. So whether you are listening to this while sitting in a century-old colonial house right now, or you just want to understand the hidden mechanics of the buildings you walk past every single day, this deep dive is going to completely change how you look at a roofline.
I guarantee it will.
And it all starts with a central, honestly mind-blowing analogy from the archives. Chimneys are not impenetrable walls. They are, in fact, rigid sponges.
Calling them rigid sponges it's the perfect starting point.
It really is.
It immediately reorients how we think about masonry.
Yeah.
We tend to think of stone and brick as these waterproof shields, but they aren't.
Because they act like massive sponges just soaking up the environment. So we have to explore how the weather physically attacks the masonry before we even touch on the fires burning inside.
Exactly.
Let's unpack the sponge concept first. Bricks feel totally solid. Why are they behaving like sponges?
Well, it comes down to the microscopic structure of the materials. Like the masonry materials making up a chimney, the brick, the concrete, the mortar holding it all together, they're inherently porous.
Okay.
They're essentially baked earth and mineral compounds. So at a microscopic level, they're honeycombed with tiny voids.
Just full of empty space.
Right. And when that coastal Maine weather hits, with driving rain, heavy melting snow, and high humidity, capillary action takes over. Those materials actively draw ambient moisture in.
Wow.
They literally suck water deep into the structure of the brick and mortar.
Which sounds problematic just on a basic moisture level. But in a place like Maine, it's not just the water that destroys the chimney, right? It's the brutal freeze-thaw cycle.
Yeah, this is where the physical environment turns masonry into a ticking clock. Water expands by about 9% when it freezes.
9%? Wow.
Right. So imagine a porous brick that has soaked up a heavy autumn rain. Then a freezing winter wind rolls in and drops the temperature rapidly.
Oh, okay.
The water trapped inside those tiny voids freezes into ice crystals, and those crystals expand.
Oh, man.
And that expansion exerts thousands of pounds of pressure per square inch from the inside out, which causes microscopic cracks in the brickwork and the mortar joints.
So it's like a hydraulic wedge just working from the inside.
Exactly.
And it doesn't just happen once a winter.
Oh, no, it happens constantly. The sun comes out, the ice thaws, and the water recedes or evaporates slightly, right?
Leaving behind larger cracks than were there yesterday.
Right. Then the next rainstorm hits. Water flows deeper into those newly expanded cracks. The temperature drops again, the ice expands further, and the wedge is driven even deeper.
It's just a relentless mechanical prying process.
Relentless.
Which obviously leads to severe structural degradation over time. The structural integrity fails, water intrudes directly into the home, you get musty odors in the attic, and eventually incredibly expensive interior damage.
Exactly.
But wait, I'm stuck on something here.
Okay, what's that?
If the brick is a literal sponge soaking up Maine rainstorms, putting a waterproof sealant over it seems like the worst thing you could do. Like, aren't you just trapping a gallon of water inside a brick, sealing it shut, and waiting for winter to freeze it? It feels like you'd rot the chimney from the inside out.
Yes, and that is the exact trap so many ambitious DIYers fall into.
Wait, really?
Oh yeah, going to a hardware store and buying a standard heavy-duty waterproof sealant will absolutely suffocate the masonry.
Because it seals it completely.
Right, you trap the moisture inside, and the next hard freeze will literally blow the faces right off the bricks.
Ouch.
So the specialized technology used by professionals is completely different. The solution relies on highly breathable waterproof sealants, usually silane or siloxane-based.
Okay, breathable sealant. It sounds like putting a Gore-Tex jacket on your house instead of a cheap plastic rain poncho.
That is the perfect physical equivalent. Think about it. A cheap plastic poncho stops the rain, but you immediately start sweating underneath because the humidity can't escape.
Right, you get soaked from the inside.
Exactly. But Gore-Tex stops liquid water droplets from penetrating from the outside because the liquid molecules are too large to pass through the fabric.
Right.
However, the microscopic pores in the material are large enough to allow water vapor to escape from the inside out.
So the liquid rain bounces off, but the dampness already inside the brick can evaporate and exhale through the coating.
Exactly. The masonry can still breathe. The brick exhales the moisture it already holds during the dry days, but it refuses to drink in any new water during the storm.
That's incredibly smart.
In a relentless, wet coastal climate, that breathable membrane is really the only thing standing between a healthy chimney and catastrophic water damage.
That sets up our next major hurdle beautifully, honestly. We know how the freeze-thaw cycle is constantly trying to pry the masonry apart with ice crystals.
Right.
But what happens when the weather actually wins? What happens when the mortar finally gives up, turns to sand, and just starts falling out?
Well, then you arrive at a critical crossroads.
Okay. You have two drastically different ways to handle a failing chimney: preservation or destruction.
Right, and the preservation route is an incredibly painstaking process called tuck pointing.
I hear that term thrown around a lot in home improvement circles. What is the actual mechanism of tuck pointing?
It's essentially surgical masonry.
Surgical masonry.
Yeah. Technicians use specialized grinders and hand tools to carefully remove the deteriorated, cracked, and crumbling mortar from between the bricks.
Yeah.
They have to grind it out to a very specific depth without damaging the surrounding brick, and then they replace it with fresh structural mortar.
Gotcha.
And because of the aggressive freeze-thaw cycle in Maine, this sacrificial mortar layer typically needs to be replaced every 20 to 30 years.
So it's not a permanent fix at all. It's a generational maintenance requirement.
Yeah, it is the cost of keeping a historic structure standing. But the benefits are massive, though.
How so?
It strengthens the existing structure, seals up the water infiltration points, and it's significantly more affordable than a full rebuild.
That makes sense.
And crucially, for a place like Portland, it preserves the original brickwork patterns. You maintain the architectural authenticity of a 150-year-old colonial home rather than replacing it with modern, sterile work.
There is a fascinating material catch here that totally blew my mind. If you own one of these older historic homes, you are likely dealing with lime-based mortar.
Oh, yes. The chemistry here is so important.
You cannot just run to the hardware store, buy modern Portland cement, and jam it between those old bricks. It genuinely made me think of performing dental work on an antique.
That's a great comparison.
Like, you can't put a modern, hardened titanium implant into an old, fragile jawbone without breaking something.
Exactly. The thermodynamics of the materials demand that delicate approach. Historic bricks were fired at lower temperatures in older kilns, so they're inherently softer and more porous than modern bricks.
Okay.
And lime-based mortar is also relatively soft. It flexes and moves. When a chimney heats up from a roaring fire, the entire structure physically expands.
And when it expands, the materials have to yield to each other.
They have to give. If you pack hard, modern Portland cement into a joint between soft 19th century bricks, the mortar is suddenly much stronger than the brick itself.
Which sounds good,
But during that thermal expansion, the modern cement refuses to yield. The pressure builds until the soft, historic brick simply shatters. The face of the brick literally pops off.
a process called spalling, right?
Exactly. To preserve the chimney, tuck-pointing technicians have to custom mix lime mortar to perfectly match the compressive strength of the original materials. It's highly specialized chemistry.
So that is the art of the save. But what about the destruction side of the crossroads? Demolition.
Yeah. Demolition becomes the only viable option when the structural instability goes beyond what fresh mortar can fix.
Right.
If a chimney has suffered severe water damage leading to a profound lean, or if years of neglect have caused the internal brickwork to collapse onto itself, tuck pointing is useless.
You have to take it down.
Right. Demolition eliminates the immediate hazards of a thousands of pounds brick column collapsing onto a roof or causing massive water leaks.
But taking down a chimney in a dense historic neighborhood isn't exactly a wrecking ball situation.
Oh, definitely not. It requires unbuilding the structure brick by brick.
Wow.
Professional teams have to systematically dismantle it while meticulously protecting the adjacent historic buildings, the complex roof lines, the landscaping below.
That sounds intense.
It is. Which is why choosing preservation through tuck pointing, whenever structurally possible, is deeply emphasized. It drastically reduces waste and environmental impact by preserving existing materials rather than sending tons of rubble to a landfill.
So we've established how the extreme weather is actively trying to tear the chimney down from the exterior. But that is only half the battle.
Right.
The chimney is fighting a two-front war. The inside of the flue harbors a completely different, much more immediate threat. We are moving from ice and rain to toxic gas and internal combustion.
Yeah, the stakes shift from slow structural decay to immediate life-threatening danger.
Imagine sitting in your living room on a Tuesday morning in July. You smell something. The archives point out that a lingering, burning, acrid, or campfire smell from a fireplace is a critical warning sign.
A huge warning sign.
It indicates highly flammable creosote is stuck to the flue walls. But I've always found this confusing. If you have a fireplace designed for burning wood, shouldn't it naturally smell like a campfire? Why is a wood smoke smell suddenly a massive red flag?
Well, the crucial distinction is the state of the fireplace.
No.
Smelling wood smoke while a fire is actively burning and drafting properly is normal.
Okay.
The warning sign is the lingering, acrid smell when the fireplace is cold. If your living room smells like an old, wet campfire in the middle of the summer, you aren't smelling residual ash.
Because ash just blows away.
Exactly. You are smelling a heavy accumulation of creosote that has permanently adhered to the walls of your chimney.
I always assumed creosote was just a fancy word for heavy soot. But if it's stuck to the walls and causing a lingering odor months later, it must be changing states.
It undergoes a drastic chemical and physical transformation. Creosote is a highly combustible byproduct of burning wood.
Okay.
When wood burns, especially if it's unseasoned or burning inefficiently, it releases unburned particles, hydrocarbons, and gases. As those hot gases rise up the chimney, they hit the relatively cooler masonry near the top.
And they condense.
Right, just like steam condensing on a cold glass window. It turns into a liquid that coats the clay flue tiles.
And then the next time you have a fire,
the heat from the next fire bakes that liquid coating. And over time, this buildup physically narrows the flue.
Which sounds bad for airflow.
Terrible for airflow. A narrower flue restricts the air, which weakens the draft. A weak draft causes your fires to smolder rather than burn hot.
And smoldering fires release more unburned gases,
which condense into more creosote. It is a vicious, accelerating cycle.
And this accumulation progresses through 3 distinct stages, right?
Yes. Stage 1 is mostly velvet-like soot, which is relatively easy to brush away. Stage 2 bakes into crunchy, porous flakes.
Okay.
But stage 3 is the endgame. That lingering, acrid smell usually indicates stage 3 creosote. It's been baked repeatedly into a highly concentrated, hardened, glassy tar.
Glassy tar, wow.
It is essentially fuel fused directly to the masonry. Standard retail chimney brushes just glide right over it.
So if a stray spark from the firebox gets caught in the draft and ignites that stage 3 glassy tar, you don't just have a fire in your fireplace anymore.
No, you have a chimney fire. The glassy tar fuels an intense, roaring fire inside the flue itself, burning at explosive temperatures that can easily exceed 2,000 degrees Fahrenheit.
2,000 degrees?
It literally sounds like a freight train inside your walls.
Which brings us to the terrifying structural collision of the inside and the outside. We talked about how the outside of the chimney handles the freeze-thaw cycle. But what happens when 2,000 degrees of heat hits the inside of those older flues?
Well, older chimneys were built with clay liners, or sometimes just bare mortar joints. When a 2,000-degree fire rips through a clay liner, the thermal shock causes the clay tiles to shatter instantly.
Instantly?
Instantly. And if the freeze-thaw cycle we discussed earlier has already created microcracks in the mortar behind that clay, you suddenly have an unobstructed path for extreme heat.
So the extreme heat escapes the masonry entirely. And sitting right up against the masonry of a chimney inside a historic home is the combustible wooden framing.
Exactly. The heat transfers right through the shattered clay and the cracked mortar, radiating directly into the wall cavity.
That's terrifying.
And through a process called pyrolysis, prolonged exposure to heat actually lowers the ignition temperature of wood over time.
Wait, really?
Yeah. So a chimney fire can instantly ignite the wooden framing hidden behind your drywall or up in your attic. You could have a massive structural fire spreading through the bones of your house without any smoke entering the living room until it's far too late.
It's a terrifying sequence of events, but the industry has developed a very specific, high-tech solution to neutralize this internal threat. Custom-fitted stainless steel liners.
Yes, steel liners are game changers.
Why does dropping a massive steel pipe down the chimney solve a problem that thick clay and brick can't?
Because stainless steel completely re-engineers the venting system. It acts as a continuous, unbroken barrier from the firebox all the way to the roofline.
Okay.
These heavy-duty liners resist the highly acidic corrosion caused by combustion byproducts, so they don't break down like mortar. Because they're a single sealed unit, they completely prevent that dangerous heat transfer to the combustible framing, even in the event of a flue fire.
And I imagine it also stops carbon monoxide from leaking through those hidden masonry cracks into the living space.
Absolutely. Furthermore, because these steel liners are custom fitted to the exact required diameter of your specific heating appliance, they drastically boost the draft efficiency.
Oh, because the sizing is perfect.
Exactly. The smoke exits faster, it doesn't have time to cool and condense, and you significantly reduce the formation of new creosote. It marries the historic, charming aesthetic on the outside of the home with uncompromising, modern metallurgical safety on the inside.
So knowing all of these compounding threats, the extreme external physics of the freeze-thaw cycle, the delicate chemistry of lime mortar, and the intense internal dangers of stage 3 creosote and cracked flues, we arrive at the practical reality.
Right.
How does a homeowner manage this without going bankrupt or accidentally burning their house down? Let's look at the economics.
Well, the financial realities of preventative maintenance are surprisingly approachable, especially when compared to the cost of failure.
Okay.
The 2026 archives show that standard residential waterproofing, applying that breathable siloxane membrane we talked about, costs between $300 and $800.
$300 to $800. What dictates the swing in that price?
The total cost is driven by the physical size of the property, the pitch of the roof, meaning how steep and dangerous it is for the technicians to set up scaffolding and navigate, and the amount of surface preparation required to clean the porous brick before the breathable sealant can properly adhere.
You know, it makes me think about the psychology of buying a high-end protective case for a new smartphone.
Okay. Yeah.
Spending $300 to $800 feels like an annoying, invisible extra purchase today when you just want to enjoy your home. But the stakes are wildly different.
Very different.
You drop your phone without a case, you're out $1,000. You let your chimney absorb coastal rain for 5 years without a breathable sealant. The freeze-thaw cycle destroys the mortar, and suddenly you are paying tens of thousands of dollars to meticulously dismantle and rebuild a historic structure.
The math heavily favors intervention. But applying sealant is only half of the preventative equation. Knowledge is the other half. Annual professional inspections are vital because the most catastrophic dangers are entirely invisible from the living room couch.
Right, you can't see shattered clay tiles or stage 3 creosote buildup halfway up a dark, narrow brick column.
Exactly. Professionals deploy high-resolution video scanning and specialized 360-degree flue cameras. They drop these cameras down the entire length of the chimney to hunt for microscopic cracks in the clay liner, missing mortar joints hidden behind the drywall, and early signs of water intrusion.
Oh, wow. So they find it before it's a disaster.
Right. They diagnose the structural health of the system before the damage reaches the point of needing demolition.
Which brings us to the ultimate warning found in the archives. The DIY danger.
Oh, this is a big one.
Yeah. Many people who own older homes are incredibly capable and handy. They watch a few tutorials, buy some masonry tools, and think, I can patch some cracked brick on the roof, I can run a brush down the flue. Why is it such a terrible idea to tackle this yourself?
Beyond the obvious physical dangers of working on a steep, icy roof, DIY repairs almost always mask hidden, catastrophic dangers.
How do you mean?
Well, you might beautifully patch a crack on the exterior brickwork, completely unaware that the internal clay flue behind it is shattered and venting carbon monoxide into your attic.
Oh, man.
Additionally, as we discussed with historic lime mortar, Maine's extreme temperature swings require custom refractory mortar for internal repairs.
Refractory mortar, how does that differ from the bags of cement sitting at the local hardware store?
Refractory mortar is specifically engineered with high-temperature bonding agents to withstand extreme thermodynamic cycling.
Okay.
Standard mortar will literally turn to powder and fall apart under the intense heat of a fireplace. If you patch an internal firebox with standard cement, it will fail almost immediately.
You can't just slap mud in there and hope for the best.
Exactly. But honestly, the most compelling argument against DIY maintenance isn't just about functional safety. It's about financial liability and compliance. Doing your own chimney work can actually void a homeowner's insurance policy.
Wait, really just the act of doing the work yourself voids the coverage? How does that work?
Insurance adjusters operate on documented compliance. If you suffer a devastating house fire that originated in the chimney, the insurance investigator will ask for a paper trail.
Right.
If they discover that you've been doing amateur structural repairs or sweeping the chimney yourself with retail tools instead of hiring a certified professional, they have grounds to deny your claim entirely.
Wow.
Documented professional inspections and maintenance generate a certificate of compliance that fulfills mandatory insurance policy requirements.
So that $300 to $800 upfront cost isn't just buying you a breathable sealant or a clean flue. It is buying you a legally documented paper trail of professional compliance that protects the entire financial investment of your home.
It is a very small premium to pay for total legal, financial, and structural security.
Let's take a step back and look at the ground we've covered today.
We covered a lot.
We really did. We started with the incredibly counterintuitive concept of a brick chimney acting as a porous, rigid sponge, constantly battling the hydraulic wedges of the freeze-thaw cycle on the coast of Maine.
Right.
We looked at the delicate surgical art of tuck pointing using historically accurate lime-based mortar to avoid shattering the chimney from the inside out. We transitioned from the weather outside to the explosive dangers inside, unpacking how unburned gases condense and bake into stage 3 glassy creosote.
Glassy tar. Yep.
And finally, we explored the high-tech modern solution of custom stainless steel liners that completely seal off the combustible bones of the house from 2,000-degree thermal shock.
It is a remarkable journey of applied physics. The major takeaway for you listening to this is that the next time you walk down the street and look up at a neighborhood roofline, you will never just see a stack of static decorative bricks again.
Never again.
You are looking at a highly complex, dynamic venting system that is constantly fighting a brutal two-front war, battling water and ice on the outside and containing explosive fire on the inside.
It completely changes the landscape of a neighborhood once you understand the invisible mechanics keeping those homes standing.
It really does.
And it leaves me with one final thought, something I really want you to mull over after this deep dive wraps up.
Let's hear it.
If a massive, towering, seemingly indestructible brick chimney is actually a vulnerable, porous sponge locked in a constant hidden state of decay and repair, what other seemingly permanent solid structures in our everyday lives are actually engaged in a quiet, invisible battle with nature while we sleep?